Hello, hello. Hello, 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 hello. Okay. Hello, everybody. Thank you for joining us today. My name is Ronaldo Pinto. I'm the Technical Sales Manager for Applied Flow Technology. My email is ronaldopinto@aft.com. I'll be hosting today's webinar, which we have titled, Is Vibration a Headache? And why did we choose this title? Because vibration can be a very complicated and difficult problem to solve. Today, we'll be presenting part 2 of the series webinar, and we'll be discussing a source of vibration called high frequency acoustic vibration, AIV. If you have any questions during the webinar, please type them in the chat room. And then at the end of the webinar, we'll have a question and answer session where I'll try to answer all your questions. If we don't have time to answer all the questions, then I'll send you an email with the response to your questions. In the agenda, today we'll be having an overview of the scope of the webinar. Then we'll be talking about a background of the source of vibrations. Then we'll be talking about the Energy Institute. And we'll have a brief discussion of the guidelines stage approach of the Energy Institute. Then we'll be talking about AIV likelihood of failure calculations used by the Energy Institute guidelines. Then we'll have a brief presentation of using AIV Spreadsheet to calculate the LOF. And then we'll be working on an example to apply the guidelines to calculate the AIV source of vibration. We'll have some conclusion, and then we'll have a question and answer session. First, an overview of the scope of the webinar. This webinar provides instruction on how to use AIV new Excel spreadsheet that was created based on the Energy Institute guidelines for avoidance of vibration-induced fatigue failure in process pipe network. We will apply the procedure using acoustic induced vibration, AIV, as a source of excitation. In part 1, we talked about flow-induced vibration, AIV. In part 2, we'll be talking about AIV. The spreadsheet will be available in AIV webpage. If you would like to receive a link to download it, please send an email to sales@aft.com. So a little bit of background. There are a variety of piping vibration sources which engineers should analyze in their system. Once you do the steady state analysis of your hydraulic system, you should consider analyzing the transient response to a transient event of your system, such as pump trip, pump startup, valve closure, relief valve open, etc. And why this? Because basically, to consider your hydraulic system safely designed, hydraulic transient response should be considered. AIV has several tools that will help you accomplish this task. One of them is AFT impulse. AFT impulse allows you to do transient analysis in liquid piping system to address cavitation and pressure surges issues. Another tool that AFT offers is AFT Impulse Module PFA. AFT Module PFA allows you to do an acoustical analysis to determine the acoustical frequency, natural frequency modes. The idea is to avoid the coincidence of the excitation frequency with the acoustical natural frequency of your pipe. Because if this occurs what's resonance, what's called resonance. When resonance occurs, the highest displacement due to vibration occur, and consequently, the probability of failure due to fatigue increases. Another tool that AFT offers is AFT Extreme. It's a recent tool, release tool, and it's the same as AFT Impulse, but AFT Extreme allows you to do transient analysis in steam and gas piping systems. Another tool that is recently offered is AFT Extreme Module PFA, and basically Extreme Module PFA is the same as Impulse Module PFA, but AFT Module PFA allows you to do acoustical analysis in steam and gas piping systems. Beyond the vibration sources described in the previous slide, AFT new spreadsheet is intended to address other vibration sources covered by the Energy Institute guidelines. One of these sources of vibration is flow-induced vibration FIB, which was treated in the first part of this series webinar. Flow-induced vibration occurs in both incompressible and incompressible flow. And what happens is that at discontinuities such as partially closed valve, bends, tees, reducers, a low frequency excitation is created by the turbulence in the flow. This type of excitation can lead to visible vibrations of the pipe and pipe supports. Another source of vibration analyzed by the Energy Institute guidelines is for pulsation, called flow-induced excitation, FIP. FIP occurs in gas system, and it happens when you have a branch connection or a flow around a component inserted in the flow stream. This causes vortices. Vortices have a specific vibration excitation, which on their own is not damaging, but if it coincides with the acoustical and structural natural frequency of your branch or your component inserted in the flow stream, then the high pulsation can occur, and consequently the possibility of failure due to fatigue also increases. The third and last source of vibration analyzed by the Energy Institute guidelines is high frequency acoustic excitation, AIV. AIV is driven by flow rate and pressure drop. These two variables, the higher they are, the most critical they become, which happens in large capacity relief, depressurizer, and blowdown systems. AIV, what happens in the AIV is that the critical pressure drop created by the pressure restriction device causes turbulent flow mixing that generates a high frequency acoustic energy shock wave immediately downstream the device. This shock wave propagates down the pipe, exciting the pipe higher order modes of vibration. So here's a schematic of what happens. We have the valve restricting the pressure flow and creating a high pressure drop in this section. This causes a turbulent mixing flow, and which causes a wave that travels down the pipe and excites the higher order modes of vibration downstream the device. This high frequency excitation generates a flexural vibration in the pipe, which is also called shell vibration, which have no visible pipe movement, but can result in fatigue, failures, and pipe discontinuities, such as branch connection, welded pipe, and supports. These discontinuities have what's called SIF in pipe stress analysis. SIF stands for stress intensification factor, which basically increases the stresses at the connection of the discontinuity with the main line. This creates weak points, and that is why when we analyze the occurrence of high frequency of AIV, we will treat the discontinuities as the weak points to be analyzed. So here's final element schematic analysis of a shell vibration. We have the shell vibration, we have the discontinuity, which is this section, this welded section connected here, and this would be where the SIF or the stress intensification factor occur. So this would be the weak point where the failure might occur due to fatigue. What makes this type of excitation most critical is that the failure can occur in a short period of time, which can even be in minutes. So due to how critical the source of vibration analyzed by the Energy Institute can become, the Energy Institute provides a public domain methodology to help minimize the risk of vibration-induced fatigue of process piping. These guidelines use an evaluation method for vibration failure possibility based on the likelihood of failure, also called LOF index. So the guidelines, the Energy Institute guidelines, provide a stage approach. The first part or the first stage would be a quantitative assessment, which is undertaken to identify the potential excitation mechanism. It gives an overall risk qualification, high, medium, or low. And whenever an excitation qualification results in high or medium score, the corresponding excitation mechanism should be subjected to a quantitative assessment, which is the second part of the stage analysis. Second, a quantity assessment is undertaken. For each of the excitation mechanism identified in the quality assessment as high or medium risk. From the quality assessment, an LOF likelihood of failure score for each mainline pipe system is obtained for the source of vibration. Here is a flow diagram of the quantity assessment applied for AIV LOF calculations. We're not going to go in detail of the calculation, but basically, first, it calculates the sum power level of the source of vibration based on the upstream and downstream conditions of the component. After that, since there can be more than one discontinuity causing being a source of vibration, it recalculates the power level of the source, considering all the sources. After that, it applies the stress concentration factor depending on the type of discontinuity you're analyzing. And finally, it calculates the LOF for each discontinuity. Then when you have the LOF, energy guidelines provide detail of on-site inspection and measurement techniques to help you refine the quantitative assessment you have just done. And finally, energy Institute guidelines also provide some corrective action guidance to reduce the risk to an acceptable level. So let's talk about how using AIV spreadsheet to calculate the LOF. The spreadsheet comes with an instruction manual with a detailed explanation for each source of vibration. It is very well explained. I'm going to open it right now. Give me a chance. So here's the instruction manual for the spreadsheet. It describes the procedure, and screenshot by and page by page, it describes with screenshots the procedure for each source of vibration analysis. The spreadsheet has a tab for each type of vibration source. As I mentioned, Energy Institute analyzes flow-induced vibration, flow-induced pulsation, and flow-induced an AIV acoustic induced vibration calculation. So there's a tab for each one of them. And as we mentioned, FIB can occur in liquid and gases, so it has a tab for each one of them. Each tab indicates in color the user input, what will be imported, and the calculation results. So in pink, you will see in the page, in the tab, what you have to input. In blue, you will see what will be imported from the program. And in yellow, you will see what will the results of the calculation, which in this case will be the LOF. So let's start an example of using AIV new spreadsheet to calculate the LOF for acoustic induced vibration AIV. We have a system that transfers steam from tank J1 to tank J6. We have a 1/4 of an inch connection downstream the orifice, and we want to know if it's in risk of failure due to AIV. So here's the connection. We have, it's a pressure gauge in connection J7. So let's first apply the quality assessment. We want to answer the following question with the quality assessment. Is choke flow possible or sonic velocities likely to be encountered? This question comes from the quality assessment table offered in the Energy Institute guidelines. And here's the question that you have to respond. If it's low or it doesn't happen, the choke does not happen, then it will obtain a qualification of low. If it happens and it's a yes, it will obtain a qualification of high as a result of your quality assessment. Another question that has to be answered is how many possible sources of vibrations are present. And a third question is how many discontinuities are present. As we said, discontinuities are the weak point to be analyzed because they have stress intensification factor that make it a critical point. So let's bring the program, the model. Here's the model, and we want to run it to answer the questions from the quality assessment. We go to results. And we will go to the sonic choking tab. it tells us sonic choking is happening in 3 points: junction 3, junction 5, and junction 6. So where it's happening, sonic choking? It's happening in junction 3, junction 5, and junction 6. Since we're analyzing this component here and we want to know if it's in risk of failure due to AIV, this source of vibration will not affect it because it's downstream. So the ones that will affect it is the one in the orifice, junction 5, and the one in junction 3 that is also downstream. So answering the questions, the conclusion of the quality assessment is choke flow possible, or are sonic flow velocities likely to be encountered? The answer is yes, sonic choke is happening. Excitation qualification is high, which means it requires a quantity assessment to make sure it's not failure, or to make the corrections needed to lower the risk. Second question that we'll be answering from the quality assessment is how many possible sources of vibration are present. As we concluded, 2 upstream the pipe connection. And the third questions that we want to answer is how many discontinuities are present. And why is that? Because as we said, discontinuities are the weak point when AIV occurs. So the answer to that question is 1 downstream the orifice. So now we proceed to do the quantity assessment. We open the Excel spreadsheet, save it with another name because we want to keep the original and from any change or corruption that it might suffer. We select the tab of the source of vibration. In this case, we'll be selecting AIV tab. We prepared the Excel spreadsheet, and I'll explain you what I mean with that. And when we open the Excel spreadsheet, we fill the required user input information. So what is the user input information that we have to fill? From the sources, we have to say, first, is there any reduction in sound level due to low noise by ball trim? If you have a trim that reduces noise in your reduction device, then you just say yes or no. The molecular weight of the fluid, of the gas. Then we refer to the discontinuities. First, the branch external diameter, the distance from the source to the discontinuity, the piping material, yes, if its material is duplex, and if it's not duplex. From the discontinuity, we have to answer, also input the wall thickness of the main line, and we have to answer a question regarding the connection, whether it's welded or not. Yes, if it's welded, and no, if it's not. So let's open the spreadsheet. The spreadsheet is called FlowInduced Vibration Calculation. Here's the spreadsheet. So the first step is to save it with a different name to avoid corrupting it. So I'm going to call it FlowInduced Vibration Calculation - webinar. second step is to select the tab we're going to work with. As I said, there's 4 tabs because Energy Institute guidelines use 4 source of vibration or 3 source of vibration, but FIB can happen in liquid and gases. So in this case, we're going to select AIV, which is already selected. And then we prefer the spreadsheet. When I say we prepare is the following. There's a section, a table called vibration sources, and we have discontinuities. So how many you have to prepare the table, and I like to do this. It's not necessarily, you don't necessarily have to do it, but I like to do it because it reduces any confusion. So how many sources of vibration we have? We say it's 2. So we delete the ones that we're not going to use. How many discontinuities we have? We have 2. So we have 1. So we delete the ones that we're not going to use. So we have 2 sources of vibration and 2 discontinuities. So now we still start filling all the pink because pink is the user input. So the molecular weight is 18. It asks the question, does sonic jerking occur? The answer is yes. The source of vibration, we said that the first source of vibration, because it's closer to the connect, so the discontinuity is the 5. And there's another one upstream that is 3. The second question to answer is, does your pressure reduction device have a low noise trim? In our case, it doesn't have it, so we put 0. And then we start filling the question, answering the question for the discontinuities. Where is the discontinuity located in the model? So it's located in junction 7. Then we answer the question, what is the distance from the source to the discontinuity? The answer was 1.54 meters. Very important that it isn't mentioned. You have to respect the units used by the Energy Institute guidelines because the relations and the equations are established using those units. Second question to answer is T. T is the wall thickness of the mainline pipe, which would be 14.27. Then we answer the third question. What is the branch external diameter, which would be 13.7 millimeters. Then another question, how many sources do we have? We have upstream 2. Is it welded? Yes. Piping material duplex? No. So we have answered all the questions that are required as a user input. So we save it here. And we're ready to continue. Now we open the model. So it's next step. We open Export Manager. We create an export sheet following the instruction manual. As I said, the manual will, in detail, will explain you how to create the export sheet. First, we have to create the export data for each one of the vibration sources. So we have to create 4 lines, 3 for the junction and 1 for the pipe that feeds the component. where we'll be exporting pressure stagnation inlet, pressure stagnation outlet, the temperature static outlet, mass flow rate through the junction. As I said, we have to respect the unit, so we have to export it in pascals, the pressure, the temperature and kelvins, and the mass flow rate in kilograms per second. Then we have to specify the Excel spreadsheet that we had selected. In this case, we're selecting AIV Calcs. That's the name of the tab in the Excel spreadsheet. And then we have to tell them where what cells is going to be exported to. So it will be cell D18 for all the first source. Then we have to export the data for each discontinuity. So the only element variable information that we have to export is the mainline internal diameter from that the discontinuity is connected to. So here's how the spreadsheet exporting will look like. The first source of vibration, as we said, we have to export 4 elements, 4 lines: pressure stagnation inlet, pressure stagnation outlet, temperature stagnation outlet, and mass flow through the junction. Then we create 4 more lines for the second source of vibration. The same information will be exported, but now it's not junction 5, it's junction 3. Junction 5, as I said, is fed by pipe 4, and junction 3 is fed by pipe 2. And finally, the discontinuity information. We create a line where we're going to export the diameter hydraulic of the main pipe, which is connected to. If you had more discontinuities, you would create more lines for the analysis. So let's open the model and create the spreadsheet. The first step is to open the Excel exporting spreadsheet. So the first source of vibration, we have to create 4 lines of the information we're going to export. So we create 4 lines, 1, 2, 3, 4. As I showed you in the graph, we will export here from the junction. From the pipe and from the junction. So the first one is the closest to the discontinuity. So this would be junction 5, the orifice plate. Then the pipe that feeds the orifice plate, which would be pipe 4. And finally, the orifice again. So then what are we going to export? Well, we're going to export pressure stagnation inlet, pressure stagnation outlet, the temperature static outlet, And finally, for the first source of vibration, we're going to export the mass flow rate through the junction. As I said, we have to export it in the same unit the Energy Institute guidelines uses, so we have to export it in Pascal. In Pascal. Kelvin degrees. And this one in kilograms per second. The spreadsheet we're going to export it to is the AIV calcs. We're going to use the same spreadsheet for all the information we're going to export. So we and then where it's going to be exported to. This would be D18. The next one would be E18. The next one would be F18. And the final one for the first source of vibration would be G18. We don't want to export the headers. We only want to export the value. Neither we want to export the units. So the next step is to create the same exporting lines for the other source of vibration, which is located in junction 3 at the area change. So we duplicate, junction. So we change the junction we're going to use. Here, it would be junction 3, the area change. The pipe that feeds that component is pipe 2. So here we check the units are correct. The only change we have to make is where it's going to be exported to. So it would be to line 19. So it would be, I have to change this. And finally, we don't want to export the header. We only want the value. Neither we want to export the units. So, and the final step to create the spreadsheet export element is where, for the discontinuity, we're going to analyze. So we hit new. It would be information of the pipe. The discontinuity, in this case, pressure gauge is connected to pipe 5. And we want to export the hydraulic diameter. We want to export it in millimeters to the same AIV cogs, and we want to export it to cell N18. And we don't want to export the header, neither the units. So the spreadsheet is ready. So we hit OK to save it. So the next step is to export to the Excel spreadsheet. So we come back to the model. We open Excel export manager. We're ready to export, but there's one final thing that you have to be careful about. Here, before you export, you have to make sure you're exporting to the Excel export sheet you want to. We said we created flow-induced vibration, and we created one with webinar extension. So we're ready. I selected currently open workbook, so we're ready to export. We hit export now, so it started exporting. So now it gives me a message saying there were no errors to the report and the export information, and this is everything that exported down, which were 9 lines of information. If we open the spreadsheet that we created, we will see that it created a new tab, Sport Guide, where it tells me the report that we just saw in the software. So then we go to AIV Calcs, and we make sure that everything was exported properly. Here's the upstream and downstream connection for each source of vibration, the temperature, the flow, the diameter external from the discontinuity that is connected to. So everything was supported properly. We're ready to continue. The next step is to view the LOF results in the spreadsheet. So we open the spreadsheet again. The resultant LOF is 1.0. So the next step is to use the Energy Institute guidelines to determine the appropriate actions based on the LOF value. As I said, the guidelines have a part where it analyzes the LOF for each one of the vibration source, and it guides you to the actions to be taken. So conclusions. In process plants with large capacity, large sound power generated by pressure relief valves or blowdown valves with restriction devices sometimes result in severe high frequency pipe vibrations. We saw that is this vibration phenomenon is called AIV, acoustically induced vibration. Energy Institute guidelines offer a screening option based on LOF concept to help minimize the risk of vibration-induced fatigue of process piping. Design options to improve a piping system's strength and integrity in the context of AIV excitation must focus on points of asymmetry, discontinuity, Any discontinuity is a weak point that you have to analyze when AIV occurs in your line, especially in LNG systems, which is AIV can become very critical. And finally, the conclusion is that AFT News Spreadsheet offers a comprehensive way to apply Energy Institute guidelines directly from your hydraulic model. As I said, if you're interested in receiving the spreadsheet, please send an email to sales@aft.com and we will send you a link where you can download the instruction manual and the spreadsheet. There's some reference I used to prepare that this webinar that I would recommend you to read if you're interested in getting more knowledge on this AIV process. The first reference is Acoustical and Turbulence Flow-Induced Vibration in Piping System by Jim Colin. The second reference that I recommend is Acoustical Induced Vibration, AIV, and Flow-Induced Vibration, AFV Analysis for the High Pressure Reducing System using Energy Institute Guidelines by Mr. Bagdork and Mr. Siri. And finally, another paper that I recommend is Acoustical Induced Vibration in High Capacity Pressure Reducing Systems by Mr. Carucci and Mr. Milner. So hope this webinar was interesting. Now we move on to the section, question and answers section. Let's see if you have any. So let me see the questions in the chat room. There's a question here that says where we can locate a spreadsheet. Well, as I said, just send an email to sales@aft.com and we'll send a link where you can download it together with the instruction manual. Okay, so apparently this is the only question. Thank you for joining us today. I hope it's interesting for you. Energy Institute guidelines are really interesting and powerful guidance on how to address vibrations. And I really recommend that you take a look at it if you are in charge of designing piping and you address the vibration issue. So what is next? You will receive a follow-up email with the link to the recorded webinar. We welcome you to join us in the next webinars at an AFT webpage. If you want to request an evaluation, just send an email to sales@aft.com, as well as I keep on mentioning, if you want to the spreadsheet, just request it at sales@aft.com. And if you want pricing information of a software, if you're in USA, it's in United States, it's posted in the webpage. And if you're in international out of US, United States, contact your local channel partner. Thank you very much for joining us today. My name is Ronaldo Pinto, and it was a pleasure being with you. Bye.